Method of sections. Nice. This method is good when you need to find the force on a given bar or just a couple of bars, a few bars, but you don't need the force on all the bars in the structure. Maybe you are not designing the structure, you just want to check the sanity of one of the elements or so, or some section of the truss, so you are not required to check all the bars. In that case, this method is very useful, and it's based on the fact that if a truss is in equilibrium, any part of the truss has to be in equilibrium. So what we have here is that if you have a bar, any bar, and the bar is under tension or compression, doesn't matter. Let's say it's a bar between point A and point B, and it has a force of tension. That will be the free body diagram of any of these bars on a truss that is under tension force. If you cut this bar in anywhere in the middle, on the side, anywhere, if you make a free body diagram of the little piece to the left or to the right of the cut, you will see the force that you have on the joint, T, and you will see an internal force here, which is the force that the rest of the bar that you remove is doing over the part that is in your free body diagram. And by summation of forces, if we say that this is the x-axis, summation of forces in the x direction equals to 0 will tell you that T minus Fi equals to 0, so Fi equals to T. Means that the internal force in along the whole bar is equal to the force applied at the joint, at the joints that the bar are connected to. Exactly the same will happen if the bar is in compression. If you have the bar and these are the forces on the joints, this is the force on the joint. Let's see, a compression force here at the joint. Same thing if you make a cut anywhere you make the cut. Say you make the cut here. You apply the forces on the free body diagram. So you will see here on the cut that there is a force, an internal force that you don't know. That is the force that this right part of the structure is applying on the left part of the structure. And by summation of forces in the x direction, it's going to tell you that C minus Fi is equal to 0. So Fi is equal to C. It's just telling you that the force that the bar is feeling at the joint is the same force that is applied in any point all along the bar. And what we are going to do is just to cut the bars that we want to find in order to show up that internal force. You say in this case we want to find the force on the bar GD. So we're going to cut the bar GD in order to see the internal force on that bar, which is the same force that the joint or the bar is applying on the joints. That's the force that we find in the method of joints. We find the force that the bars are applying on the joints, which is the same force that the joints are applying on the bars. In order to see that internal force on the bar GD, we need to make a cut, a complete cut that separates completely the truss in two. We're going to do a cut like this. Let me make some cleanup here. So in this case, let's say that we want to find the force in these three bars. Oh, let me erase this too. I'm gonna make, let's say we want to find the force in these three bars, CD, GD, and GH. So we make a cut like this, and the truss will be divided in two pieces. One on the left, one on the right. Let's draw the bar on the left. That's the free body diagram of the left. If I cut the bar GH, I will have a little piece of the bar here. I cut the bar GD, I will have a little piece of the bar here. And I cut the bar CD, I will have a little piece of the bar here, right? And now I will put the forces applied on this. This is a free body diagram of the left part of the truss. I will have the force of 1000 newtons here. I will have the force that the bar that I remove on the bar GH, this part of the bar will apply force here at the cut. The bar GD, the part that I erase, is applying force on the bar that is remaining on my diagram. And same thing for the bar CD, there will be a force here. So those three red forces are the internal forces of the bar CD, GD, and GH. So I can call this force CD. I will call this force GD, and I call this force GH. So I have here a free body that is supposed to be in equilibrium, because if the truss is in equilibrium, any part of the truss will be in equilibrium. This free body has to be in equilibrium in the x direction, y direction, and rotation. So we can apply three equations of equilibrium. So we can find up to 3 unknowns. So the method of sections is based on the fact that you have those 3 equations. So you better try to make a cut with only 3 unknowns to make sure that you can solve for all the unknowns. Eventually, you might be able to do another unknown if you are lucky and can set up equations that allow you to solve for the unknown that you want. In general, if you cut only, if you make only 3 cuts, well, you are sure that you can find the 3 of them. So let's continue with this one. And as you see, we took here the left part of the truss because there is no reactions here that I don't know, so I can calculate directly. I could have used the right part of the truss, but I will have the unknowns on the reactions, which I can do also, and I can find the reactions using the free body diagram of the whole structure and calculate the reactions initially before I start to cut the truss. If you want to do that, that's okay, but that's more job. In this case, I can do it directly with the left part, and I don't need to calculate those. There will be cases in which you cannot help it. You have to solve for the trusses, because no matter what kind of code you do, you will have some reactions to calculate. Okay. So let's calculate here. I guess. What will be the best way to start here? We can start by a summation of forces in the y direction, for example. Or we can start, I guess that will be the easiest way. If we make a summation of forces in the y direction, this unknown is the only one that has component in the y direction, so that will be an easy equation to do. Summation of forces in the y direction equals to 0, positive going up. We have, in this case, the angle is 45 degrees because it's 2 meters horizontal, 2 meters vertical. So all these angles are 45 degrees, 45 degrees, 45 degrees. So FGD sine of 45 degrees minus 1000 newtons from this force here equals to 0. So FGD equals to 1000 divided by sine 45. Somebody can tell me how much is this? 1000 divided by sine 45? No, I couldn't. 14.2 newtons. All right. Okay, we have GD already. What other equation we can do now in order to calculate another unknown? Solve for x. I wouldn't do that because I have two unknowns with X component. So I want an equation that is easier than that one that only involves one unknown. Some of moments about G. All right, where is G? Where is G? Where is G? Yes, G is here. That will be a good point. And you know, okay, that will be a good point.
Does it matter if the moment is on any point, or does it specifically have to be G?
No, no, any point. And you know, let me do some trick here to show you. Or let's do this one really quickly, and then we do another point. No, it can do any point in the universe. Any point in the universe. Let's do this one for point G. Summation of moments on point G equals to 0. I'm gonna do positive in this direction, so I have FCD directly. So FCD multiplied by 2 meters. This is 2 meters, right? And this is 2 meters, and this is 2 meters. Okay. Minus 1,000 newtons multiplied by 4 meters equals to 0. Therefore, FCD equals to 4,000 divided by 2 Newton meters divided by 2 meters equals to 2,000 newtons. Positive. So this is tension, and this is also tension, right? Look, let's try something different. I guess everybody got this one. Look, what happens? Let me try to erase some stuff here. FGD. FGD is here. FGD. And then I have CD here. FCD. FCD. Look, I can do this. You see this point here? That point was called D. This is point D. We can do summation of moments about point D in order to calculate FGH. How about that?
So it doesn't matter if we work from the right side of the trusses or the left side of the trusses?
Doesn't matter. Doesn't matter. And this point D is outside of the truss. Doesn't matter. The truss is in equilibrium, so it has to be in equilibrium with respect to any point in the universe. As long as you have the dimensions to get to that point, you can calculate the moments and you can set up the equation. So here's summation of moments about point D equals to 0, and I'm gonna do positive in this direction, FGH times 2 meters, plus, right, plus 1,000 newtons. Somebody can tell me the distance from the 1,000 force to the D point?
6 meters?
In meters, how many?
No, 2 meters.
From the force of 1,000 newtons to the point D.
Isn't it the distance from the line of action? So it would be
right.
2.
Let me draw the line of action. Let me put the line of action here in. Let me see.
Yeah, but the line of action would be horizontal in this case, wouldn't it be? So it would be 6.
We're talking about the line of action of the 1,000 force. Let me put it here in green. This is the line of action. You see it? This is the line of action. Now I need the distance from this green dotted line to point D. That line, that distance will be this distance here, from here to here. Right, Candela?
Oh, I got it. Thank you.
4, 6. Right? This is the distance from the point, right? Well, actually the force was down here. Don't get confused for that fact that the force was down here and the point was up here. The line of action is this one. I mean the distance is that one. You guys struggle a lot with that. I had a office hours with another guy. Yeah, I know many people struggle with that. Be careful. It's not this one. It's not this one. It's moment of force with respect to a point is F times D, where D is the distance from the point to the line of action of the force. I don't mind repeating myself about this. This is the force. This is the force. This is the point. Just thread the line of action. So this is the distance. Where this is 90 degrees. All right. Very important. Very important. So we said that the force of 1000 has, and that distance is called the lever arm, 6 meters. And no more forces apply moment with respect to point D because this one goes through the point, so doesn't have any distance. So distance is 0, that's why this force doesn't apply any moment here. And this force also passes through the point, so there is no distance between this force and the point, so the moment is 0. I could put it here on the equation, FGD times 0, but there's no point, plus FCD times 0 equals to 0. You don't care about this, right? So now we have FGH equals to 6,000 Newton meters divided by 2 meters equals to 3,000. Actually, this 1,000 times 6 meters goes to the other side as a negative number, right? So it's minus 3,000 newtons. Compression, you get a negative number, so this is compression. Okay. So we have FGH, FCD, FGD. Completely solved for those 3 bars without going through the method of joints. We don't have to, in order to find this, what the method of joints, we'll have to solve for A. You solve for the joint A, then with joint A, you have this bar, and then you can come to joint B and solve for this bar, and then you have to come to this F, so you can find this bar, and then you have to go to C in order to find this one, and you have to find this one too in order to come down to point G to solve for GD and GH. So you have to solve 1, 2, 3, 4, 5 joints in order to find the 3 forces that we wanted. Here, just making the cut with 3 simple equations, we solve the problem. That's the beauty of the method of sections. Of course, the method of joints is good because you find all the forces on all the bars. But if you just need a few, this is what you will do. So we just have to make more examples. Let's see, let's make another example. Can you go back, please? So with this method, we can just ignore the other joints. Yes. In this method, this method is useful when you want the force on just a few bars and you don't care about the other bars. Imagine that there was a problem on those bars, some termites were messing with those bars, and you have to replace. You want to make sure that the force on those bars is okay. So you just want to know only the force on a few bars. Then you use the method of sections because you don't need the forces on the rest of the bars.
So the problem was only asking for 3 forces?
Yes. Yes, the problem was only asking for those 3 bars. What happened if for some reason, I just want to show that it's the same if you calculate this using the right side of the truss, not the left side. We need to use, for some reason, we need to use this side. So in that case, we need to calculate the reactions. we need to calculate the reactions here in order to solve for this. But this will be just to show you that you can choose any side you want on your cut, and you should get the same results. So let's calculate the reactions here really quickly. Let's do a free body diagram of the whole structure. And this distance is 2 meters. So very easily summation of moments. Oh, this is point E. This is point I. Summation of moments in the E point equals to 0, positive like this, will give me that Ri times 2 meters minus 1,000 times what? Let's see, we learned the lesson. 1,000 times what? Anybody dares to tell me what is the lever arm of 1,000? 8 equals to 0. So Ri equals to 8,000 divided by 2 newtons meters over meters, 4,000 newtons. 4,000 newtons. So this is 4,000. I got positive, so the direction that I assumed was correct. Now summation of forces in the x direction equals to 0. I'm gonna do positive in this direction, so I have Ex minus 4,000 equals to 0. So Ex equals to 4,000 newtons. So that's Ex here, 4,000. I got a positive value, so the assumption that I did is correct. And now, a summation of forces in the y direction equals to 0. I'm gonna do positive going up. Then Ey minus 1,000 equals to 0. So Ey equals to 1,000. I got positive. It means that I got it in the right direction. So Ey equals to 1,000 newtons. So I got the reactions complete. Okay, so now let's take the right part of the structure in order to do the method of sections. Now we have, so I have the internal forces. This force will be F dg. This will be force F cd, and this will be force F gh. The same forces that we find in the previous cut. I am going to show you just that is the same. No matter which section you take, you should get the same results. Then I have here 4,000. I have here 4,000. And I have here 1,000. Now we're going to find the same three forces. This distance is 2 meters. This distance is 2 meters. And the angle is 45 degrees. So summation of forces in the y direction can give me a dg. Summation of forces in the y direction is equal to 0, positive going down. So I would say f dg cosine or sine, sine of 45 degrees minus 1,000 equals to 0. So f dg equals to 1,000 divided by sine of 45 degrees equals to, actually is the same operation that we did back here, right? So we get 1,414 divided by 2. We got positive, so this is tension. Good. Now we can do summation of moments about the point D to find FGH. Summation of moments about point D equals to 0. Positive, I'm gonna do positive like this. I always choose the positive direction in order to get the unknown with positive on my equation. So I do here FGH multiplied by what distance? Somebody can tell me in the chat. Oh, sorry, question. Could you have done summation of forces about A to solve for EY? Summation of what? Mark? Could you have done summation of forces about A? Well, summation of forces doesn't go about a point. When you say summation of forces, you have to say forces on the X direction or on the Y direction. When you say summation of about or moment, summation of moments about 8 for EY. For EY. Yes. Yes, you can do that. Actually, let's verify very quickly. This is an interesting point. Summation of moments about point A. What is point A? Yes. This is point A here. For EY. That's an interesting. Let's make a little parenthesis here. I'm gonna do it up here at the top of the screen. Interesting. Summation of moments about point A equals to 0. I'm gonna do positive in this direction to get EY. So I get EY multiplied by 8. And then I have minus EX, which is 4,000 multiplied by 2. And that's it, equals to 0. So EY equals to 4 times 2 is 8,000 divided by 8. So you get 1,000, right? 1,000, the same value that we got using summation of forces. All right? Let's keep going. You're welcome. Let's keep coming back here. We were doing summation of forces, summation of moments about the D point, positive in this direction, in order to get point D. Where is point D? Okay, so it was going to be FGH multiplied by how much? GH multiplied by 2, perfect. That's moments about the ED point. 4,000 produces moment in the same direction, so positive. 4,000 multiplied by 2 also, right? Minus 1,000 times 2 equals to 0. FGH equals to 1/2 of 2,000 minus 8,000 equals to 1/2 of 6,000 equals 3,000. Oh, negative, right? Negative 3,000. So we get compression. Okay, you saved my life, Oliver. Thank you very much. And Oliver and Emily. Thank you, Emily. So 3,000. 3,000. 14, 14. 14, 14. And are we missing something still? Okay, still we're missing. Well, we have GH. We have this. Well, we are missing FDG, right? No, no, CD. We're missing CD. CD. Summation of forces in the X direction will give us CD. Positive in this direction, FCD plus FGH, which is 3,000, but compression, plus 4,000 minus 4,000. CD. I guess I don't know what I'm doing here. What is CD here? Do you find CD? Am I missing? Oh, I am missing also here the force dg cosine plus force dg. Force dg is 1414.2 cosine of 45 degrees equals to 0. I hope that works. So FCD equals to 3000 goes positive to the other side, minus 1414.2 cosine 45. If I'm not mistaken, that's 1000. 1414.2 times cosine 45 equals 1000. So FCD equals 2000. I got positive, so so it's tension. Okay, we got it. 2000, 2000. Whew. All right. Okay, so method of sections. You cut your truss. You use either the left side or the right side. Doesn't matter which one you use. Of course, you will use the one that requires less work. So in this case, was easier to do the left side because you don't need to calculate any reactions. You have already all the forces in order to solve for your unknowns. But if you use the right side, it's the same thing, but you have to calculate the reactions, right? But you get the exact same results. You get to use to set up your 3 equations. In order to find your unknowns, you can play with the point that you use for your summation of moments in order to get the easiest equation that you can, and summation of forces when it's better than summation of forces than a summation of moments. Be careful. Moment of a force with respect to a point is force times distance. The distance has to be perpendicular to the line of action of the point. Don't forget that. So you solve your trick, or you can make a decomposition of your force in order to get the components that give you easier distance. Sometimes there is not so easy to find out what kind of cut to make. Not always is that as easy as this is case that I suppose here. I just wanted to show you how the method works. So I give you an easy example, so you don't get lost in the nitty gritty of a complicated problem. But let me show you here a problem that is not as obvious. How about this problem? Determine the force in members A, F, and EJ of the truss shown when P equals Q equals 1.2 kilonewtons.
Professor, I have a question.
Yes.
So for the last problem that we were doing, we basically have to solve like the first section that we did, like for the forces of CD, GD, and GH, right? The rest was just for you to show us that you can do it from any point.
Right.
Okay.
Right. Yeah, I did the whole problem first using just the left part of the truss, and with the left part of the truss we solved for the 3 bars that we wanted, and then that's the end. We don't need anything else. But then I did it again for the whole, was using the right part of the truss, and I did the whole problem with the. Let me show you. Let me put it here on a. Here is what I just did, right? So I did the problem twice. You don't need to do it twice when in a given case. When I give you a homework or when you are in real life, you only do once, either the left side or the right side. Okay. You guys are solving for the exact same bars or same unknowns, but here I just did the problem twice. Okay, this is another problem. Determine the forces in members A, F, and EJ. So the problem is asking for the force on this bar and the force on EJ, this bar. So now the problem is how to cut this truss in order to see the force in those bars. If I cut this bar like this, I will have too many unknowns. There will be no way to find that out, right? If I cut this with so many bars, it will be crazy. I will have so many unknowns. I will have a force here, another force here, another here. So there is no equation that I can set out to solve so many equations. So I mean, so many unknowns. You have to cut your truss in a way that you can find a good summation of moments that eliminates some of the forces and leave remaining the force that you want to find, and that is not too complicated. I'm gonna show you what is the cut that you should make here. If you want to find this force and this force, EJ and AF, the suggestion is to make this cut. Okay? I guess we have to finish here is A15. Let's up to A15, right? I am gonna leave you guys with this suggestion. I suggest you to make the cut, draw either the top part of the truss or the bottom part of the truss, whichever you like best. I guess it's basically the same. Maybe it's easier if you work with the lower. No, the same. Anyway, you have to solve for the reactions, because if you use the top part of the truss, you have to use these reactions, and if you use the bottom part, you have to use these reactions. So it's kind of similar. If you use the lower part, you have to use one reaction here and two forces here. And if you use the upper part, you have to use two reactions here. So it's very similar. In any way, you have to use reactions. So first thing you have to use is to find reactions. That's first thing you have to do. And then you decide to use either the top or the bottom. What I suggest to you is make the drawing. Make the drawing of your it will be something like this. If you use the top part, it will be something like this. This will be the cut. That will be the cut. And then I'll leave you to put, this is your free body diagram. What is missing in this free body diagram is the forces. You have to put all the forces on this diagram. Well, I suggest you put the dimensions and think about a point where you can find an equation that allows you to find your unknowns. Can you cut AB, AG, AF, AB? Oh, okay. I was going to talk about that. AB, what did you call AB, AG, AF? The problem with cutting here is a very good question. Actually, I was going to talk about this cut. If you cut about this, what you are isolating a joint. So this is just the method of joints. And with this joint, you cannot find the forces because you have one joint with three unknowns. So you cannot do, you cannot, you will be getting into the methods of joints. And this is not a good joint to start because you cannot solve it. Remember, in joints, you only can have two unknowns. And in this case, you will get a joint with three unknowns. So not good for that side.